Thank you. Okay. Next up, let's welcome together Erethon, who's gonna take us around the RF world in 60 minutes.
Thank you, everyone. Hello, my name is Dionysis. First of all, I would like to thank you all for coming, and also thank the organizers for having me, and all the volunteers for helping run the conference. If you scan the QR code, it's going to take you to the slides. If it's easier to view them on your phone, feel free to. So, as I said, I'm Dionysis. Online, I go by degree or Erethon, depending on the context. My website is up there. I'm an SRE by trade, so sysadmin, DevOps, whatever. I'm a hacker at heart, so I like to tinker with things. I like to tinker with electronics. I like to tinker with wireless technologies in particular. And I'm also a radio amateur, so that's my call sign up there as well, and my contact information. Today, I'm going to be talking to you about radio waves and how it's a fascinating world that is all around us, but it's invisible. We can't perceive it, but it affects our daily lives. So then for the next few minutes, I'll be talking about science and history of radio frequency. So sorry if that bothers you. I think it's important so that we're all on the same wavelength. So what is radio waves and what is electromagnetic radiation? The term for electromagnetic radiation is waves that are fields of electromagnetism that propagate through space. When you have current passing through a conductor, like a wire, this generates a magnetic field and an electric field around the wire. And if the current is AC, if it's alternating current, it is oscillating, and those oscillations translate to electric and magnetic fields that move through space. So those are the waves. This is the classical way to view electromagnetic radiation. There is a quantum version of it. I can't explain it. It's tiring my brain even reading Wikipedia page about it, so I'm not going to go into it. And these waves, they're propagating at the speed of light in a vacuum. In Earth's atmosphere, they're also pretty close to the speed of light, so we're going to consider it the same. And we usually apply this current in an antenna because antennas are good at releasing this radiation outwards. So first of all, the electromagnetic radiation, they were first theorized by James Maxwell in 1865. He published a book with his equations that specify these things. Later on, they were demonstrated as existing and actually verified that they exist by Hertz in 1887. And the first practical application was done by Guillermo Marconi in 1894, where he transmitted some Morse code from one end of his backyard to the other. And Marconi was an inventor and also a businessman, so he created a company to try to bring this technology to the market. And there is an interesting side story here that he had trouble patenting it because his patents infringed on patents of others. He was able to patent it in Europe, but he couldn't in the US. And his patents also infringed on patents of Tesla, particularly in wireless energy transmission. And there is a lot of history there on who first invented radio waves, if it was Marconi, if it was Tesla. Go read up on it if you want. It's interesting. In the end, the history books have Marconi as the inventor, but there is also interesting things because he had backing by banks while Tesla lost his backing, so it's interesting. And the first application that he wanted to use for that was to communicate with ships, because ships back then, when they did cross-Atlantic trips, they didn't have any way to communicate with the land. And only 14 years after his first practical application, in 1908, the Titanic sank, and on it there was a transmitter by the Marconi company. They managed to transmit an SOS signal, and so 700 people were saved out of the 2,000-something that were on board. And Marconi was hailed as a hero that his invention saved 700 people. So for electromagnetic radiation, we particularly care about one thing, that is frequency, that we measure in hertz for a signal and the radio wave. And we also care about the wavelength, which is we measure in meters. These two are connected. The formula to get it is this one. The Greek letter lambda, L, is the wavelength. U is the speed that the wave is traveling in whatever medium. For us, it's going to be the speed of light. And F is the frequency of the wave. So we can see that as the frequency increases, the wavelength decreases, and vice versa. And based on the frequency of electromagnetic radiation, we put it in a spectrum. Starting from the far right, we've got 0 hertz, and moving to the left, we're increasing in hertz in frequency. We'll only be talking about this part. These are the radio waves, so starting from 0 or 3 hertz to up a couple terahertz maybe, or 300 gigahertz, depends on where you draw the line. We first have radio waves, then we have microwaves, then we have infrared light, and then we have visible light, because light is also electromagnetic radiation, ultraviolet light, X-rays, and then gamma rays. What we're going to be discussing, radio waves, is non-ionizing radiation. This means that the radiation doesn't have enough energy to ionize atoms or molecules, so they are safe for humans. And all of us are currently transmitting electromagnetic radiation. Anybody in the universe that has temperature above 0 Kelvin is thermally radiating. This is also infrared radiation. There is cosmic background radiation. There is noise from all of our electronic devices. My phone, my laptop, anything is currently radiating. If it's interfering, we're calling it electromagnetic interference, EMI. There was a talk on the first day by Goran. It's very interesting to learn about EMI if you wanna. I suggest you do that. Go watch that talk. And this is a photo, this is a screenshot of the spectrum currently from almost 90 to 98 megahertz. This is the FM stations in Athens. Every peak we see, that's a signal, that's an FM station. And the horizontal line is the summary, it is the sum of all the signals, all the background noise. It's the noise floor, that's the noise. If we compare this to a bar, to give an example with audio, if you were in a noisy bar, all the conversations, all the music that's playing around you, if you sum up all this noise, that's the noise floor. And in order to hear someone, they need to be talking above that noise. So they can be right next to you, and they can be whispering, and that's loud enough for you to understand, or they can be on the other end of the room, and they need to be shouting. But if the lines, if the peaks are below this horizontal line, we wouldn't be able to pick them up. So if I go back to this, these peaks, they take different area of the spectrum. So we can't have them be in the same space. We say that the spectrum is a finite resource. A signal cannot occupy the same area as another signal. That's not so true anymore. We have ways to combine signals, but in the past, this was the case. We believe that it was a finite resource. There is so much RF you can fit on it. And we needed a way to coordinate all of this. So in 1865, ITU was established. ITU stands for International Telegraph Union. Didn't have RF yet. That was for the telegraph only. There was a union to coordinate all the telegraph operators. And after World War II, after the United Nations were established, it became part of it. And ITU nowadays stands for International Telecommunication Union, and they publish the ITU radio regulation. This is an international law that specifies and regulates the spectrum from 9 kilohertz all the way to 300 gigahertz. Countries need to follow and enforce this. And ITU specifies that spectrum is an exclusive property of the state. So every country, it owns its own spectrum. This is very interesting, again, for me, because it's weird to say that countries own something that should be most likely in the commons. There is the spectrum commons theory, if you want to read up on it, that specifies that the spectrum belongs to everyone and countries can't own it. The first attempt at a country owning the spectrum was in 1910, where the US Navy attempted to regulate radio frequency. And in every country, we have a state office that is responsible for it. In Greece, it's EET. It stands for Hellenic Telecommunications and Post Commissions. This is for the post office. It started as a post office part of the state, and because communications are considered important enough and part of the post office, it got added there. In Serbia, I think it's Ratel. I think it's the same for you. It started for post office again. In the USA, it's the FCC. In other countries, it's a different office. So on the legality of radio equipment, it varies wildly by country. Check your local laws. As an example, in Greece, you can't own radios if you don't have a specific license to own them. It doesn't matter if you use it to only listen. You can't own them. That's it, the end. And historically, governments and the state wanted to control radios. So as an example, during the Nazi occupation in Greece, there was a single radio station in all of Greece that was saying the news pretty much, and they took control of that, and they also took control, they tried to get access to all the receivers that people had in their houses, lock them only to that frequency of the state station that was now broadcasting propaganda for the Nazis, and they find anyone that had an unmodified radio or a modified radio or a radio they didn't declare. They didn't do it successfully, but they were trying to do that. So this is something that historically the state is very interested in. And I think that the situation today is very blurry because the laws haven't kept up with the technology at all. Like, for Greek law, the radio is still something that was defined as it was defined in the 80s. Nowadays, radios are something completely different. So if the ITU specifies who can transmit and how and when, how do we do it? How do we have Wi-Fi? How do we have Bluetooth, etc.? So one way to transmit is to pay for the right to transmit. You pay your state, you pay, for example, in Greece, to own a TV station or a mobile carrier if you are, or a radio station, whatever. You pay a license to transmit specific frequencies up to a specific power level and for a specific type. For commercial reasons, you have to have a specific license. So it's everything is owned by the state. Otherwise, you can get licensed as a radio amateur operator in your country. Usually, it's something very simple. It's a test that you take. Maybe it's a practical one. Maybe it's only theory. In Greece, it's only theory nowadays. So you get a license from your state that allows you to transmit at specific frequencies, again, and with specific power levels. Maybe your line of work allows you to. If you are a firefighter, for example, or a police officer, you are given access to a radio and you are allowed to transmit. Otherwise, you might be on a boat, and the boat might have a radio license to it. So the boat is allowed to have the radio, and anyone on board is allowed to use it. Or you might transmit in a part of the spectrum that's free for everyone to use, under specific conditions. So which parts are those? These are the ISM bands. Back in the 1940s, we realized that we can use microwaves for heating. So we realized that, hey, if we transmit a signal at 2.4 gigahertz or about, water is heating. So that was controlled by regulations back then. We couldn't transmit to heat things. So they decided, hey, let's open up the spectrum a bit. Let's allow some industrial, scientific and medical purposes in some specific areas of the bands. No telecommunications allowed, but you are able to use them to heat things, for example. And this is a bit obsolete nowadays because Wi-Fi, Bluetooth, Zigbee, LoRa, everything that we have is pretty much, besides phones, everything is on those ISM bands for most of the part. And as we said, antennas are important in transmitting and receiving signals. They come in all shapes and sizes. The antenna that we have to use, the size of it depends on the frequency of the wavelength of the signal. Generally, we want to have between 1/4 the size of the wavelength and up to the size of the wavelength, but that depends. So, for example, Bluetooth and Wi-Fi that work at 2.4 gigahertz, the antenna can be from 2.5 centimeters all the way to 3 or 4 centimeters. For analog FM broadcasting, so radio stations, which they are around 100 megahertz, the wavelength is 3 meters. So 70 meters of cable is enough. This is why we can't listen to the radio in theory from our phones because they're not big enough, but if we connect a headphone jack, we can use that as an antenna to listen to the radio stations. And on the extreme side of it, on the lower side of it, submarines in the past used to communicate, the US submarines at the very least, used to communicate with land at 76 hertz. The wavelength of that is around 4,000 meters. For reference, 4,000 kilometers. For reference, the circumference of the Earth is 40,000 kilometers. So we need an antenna 1/10 the size of the circumference of the Earth. That's weird. And in the end, they built cables that went 70 kilometers in distance, that they were acting as antennas. And the submarines used to drag a cable up to 200 meters behind them, just as a receiver only. They couldn't transmit, but they could receive. And here are some photos from antennas. This is from a hill in Athens. These are point-to-point 2.4 antennas. This is an LTE GSM antenna in Novi Sad. What I find interesting is that you have the antennas out in public, In Greece, in Athens, people are afraid of antennas, so we try to hide them, specifically the LTE antennas. So we put them in boxes that look like chimneys at the top of buildings. Some satellite dishes in the BBC of Scotland, because they were big dishes and they seemed interesting to me. Satellite dishes are also antennas. Same idea, smaller antenna. Under this dome, there is a small satellite dish that rotates, that is able to rotate. They are used in ships commonly. This one in particular is used for television for the crew and the passengers. And this is in Belgrade. These two are RFID antennas. I believe they are used to allow access to specific parts of the streets. They raise and lower bars for cars that have the specific tag on them. And as we said about the size, this here is a Bluetooth antenna. It's the squiggly line at the end, this part. So that's all of the antenna. So how do we explore and how do we capture this world? How do we view it? A big note of warning here, anyone can transmit RF. They might have a license, they might not, but for whatever reason, anyone can transmit radio waves. So they are by definition untrusted input. If you're capturing it, if you're parsing it, be careful because it's security one-on-one. You don't parse and you don't trust untrusted input. Lots of radio-related software also was written in not memory-safe languages or with security in mind in the past. Some of the ham radio things are written in the 90s. Just a warning, think about it before moving forward. And for hardware, there is hardware that's built to receive and transmit signals for specific frequencies, specific modulation, specific signal types. Usually they are locked down and you communicate with it over USB or a higher level interface serial or something. And there is hardware for everything, for Bluetooth, Wi-Fi, Zigbee, LoRa, anything. As an example, a simple receiver and transmitter for LoRa. This can do LoRa and can do other things as well. And historically, we used hardware to receive things. And hardware is expensive. Hardware is hard. You have to do a lot of math for radio things in hardware. And that's, again, hard and expensive. And so at some point in the 1980s, they had the idea that, hey, maybe now that we have computers that are fast enough, we can have a dumb receiver that only captures the signal and digitizes it in some form, passes it on to the software on computer. And then the computer can do all the smart things, demodulate the signal, do all the digital signal analysis, demodulation, decoding, whatever. And nowadays, this is pretty common, and it also works on smartphones. Our phones are fast enough to do these things nowadays. So again, this happened in the late 80s, beginning of 90s. It was still expensive, very expensive equipment, tens of thousands of dollars. But something happened that changed all of this. Some people figured out that you can use cheap USB digital TV receivers that cost around 20 to 30 euros back then, and you can get the raw data out of them. So they wrote a driver, it's called RTL-SDR. The rest is history, I want to say, because it's quite common nowadays. This is what they used to look like. This is mine from back in 2013. Just an antenna connection at the back, USB at the front, and you have to do everything then on the computer. All the magic happens on the computer. On the software side of things, there is GNU Radio, which is the golden standard for doing anything with signals. It requires you to know what you are doing. So this is what it looks like. You have these block diagrams that you can connect. You can connect the output of one block diagram to the input of the next. It gets complicated really fast if you don't know what you are doing. I suggest you don't start with it, but look at it from the start. Just have an idea that it exists, it's out there, experiment with it. But to get started, I recommend something like this. There is SDR++, GQRX, Cubic SDR. This is a screenshot of GQRX. Multiple software exist. Some are open source, some are not. Pick and choose whatever you want. And on the analyzing signals, there is Spectrum and the Universal Radio Hacker, which are very good for inspecting and reverse engineering signals. And there is also RTL-433 that can decode a lot of chip sensors and a lot of protocols. Currently supports 263 of them. We're going to see more details later. And of course, I have to mention this nowadays. Flipper zeros are everywhere. I think almost every second presentation in BalCCon has mentioned them. They're a gamified and handheld solution. You can use them to do sub-gigahertz. They can do infrared. They can do a lot of things. It's a nice device to experiment with, I would say. They are NFC compatible as well. As I said, smartphones work. This is my phone. You can just plug in an SDR. The black thing at the end is an SDR receiver and an antenna. The software is SDR++. Smartphones are fast enough for this. And finally, there is the HackRF, which is a standalone SDR that you can also use with PortaPack. PortaPack is an add-on board. It has an LCD screen. It has a couple of knobs. It allows you to use it in a handheld way without a computer. And now on the privacy part. So as we said, if current passes through a conductor, it's creating some form of a wave. Most electronic devices transmit some kind of signal nowadays on purpose. This is for them to work. My phone is using Wi-Fi to access the internet. My phone is using LTE to have calls. This is done on purpose. However, there are also emanating signals that are not done on purpose. This is the EMI, electromagnetic interference we mentioned earlier. It's out of topic for this talk, for this presentation. So Tempest, which is an acronym of an NSA code name and a NATO specification, it stands for Telecommunications, Electronics Materials Protected from Emanating Spurious Transmissions. It's a mouthful. The TLDR is that the NSA figured out that, hey, if a device is transmitting unknowingly, maybe we can capture that signal and find out what the device is doing. There are demos of people being able to use SDRs to recreate what's shown on a laptop LCD screen. So it works. And the NATO specification is the other end of it. It specifies how devices should be protected from this, how they should be designed, how they should be cased, whatever, to protect them from this. So anytime a device is transmitting, it can be located. You can't get around this. If you're transmitting, you can be located. The simple example of this is having two receivers. You can, with the two receivers and the transmitting device, you can triangulate the source of the signal. You can figure out where it's coming from. Nowadays, we have Kraken SDR, which is a relatively cheap SDR. It has 5 SDR receivers in it and 5 antennas. You place the antennas in a specific pentagon pattern, and based on the difference of the speed of the signal each antenna receives the signal, you can figure out the location of the direction, at the very least, of the transmitting device. And if you keep moving, you can figure out where they're transmitting from. And if you start doing research for privacy on wireless communications, you're going to find out pretty soon that most of the people, even if you search for privacy, they focus on security, not privacy. So they care about the content of the communication most of the time. They care that you can't eavesdrop on the communication, but not if you can identify who the person that's using it or locating the transmitter. I'll mostly be focusing on this, the privacy side of it, and not the security. So the big elephant in the room currently is the phones that we have on us. For a lot of years, people were afraid that you can track someone from their phone. That is true, you can do it. And I'm not going to be paying too much attention on them, at least on the LTE signal, the signal that's used with the provider, with your phone provider, because there are better signals that are easier and faster and simpler to follow and track. So yeah, not the easiest signal to capture. It's relatively easy, but there are way easier technologies to use. In my opinion, Bluetooth is the worst offender of them. So Bluetooth got released in 1998. The classic Bluetooth, which is also called BR/CDR, basic rate and hash data rate. In 2011, we got Bluetooth 4.0, BLE, Bluetooth Low Energy, as we commonly call it today. In 2014, 4.2 got released, and in 2016, Bluetooth 5 got released. In Bluetooth 4.2, they had some very good privacy protections because they realized that these devices are transmitting and they are identifiable. But most devices nowadays fail to properly use them. So every Bluetooth device has a BSSID, which stands for Basic Service Site Identifier, that uniquely identifies the device. Most devices don't properly use BLE 4.2. For example, my smartwatch transmits the same ID all the time. Wherever I go, my smartwatch is transmitting. And I can't turn off Bluetooth because that's not a feature that the company provides. And even if some devices properly use the privacy protections of BLE 4.2, they fail in another way often, where they hard code the serial ID of the device on the name of the Bluetooth device, which again, most often you can't change. And they're practically everywhere: headphones, smartwatches, everywhere. Mice, keyboards, microphones, whatever. Bluetooth is everywhere. This is a screenshot from an application in Google Play. It says that it has more than 5 million downloads, and it's an application for a smart toothbrush. So it's an application that connects with your toothbrush over Bluetooth and lets you know for how long you brushed your teeth. But the problem is that the Bluetooth only works whenever the toothbrush is on, from what I've seen. So all your neighbors as well know when you brush your teeth or for how long. They might not know the exact contents, but they know that the toothbrush turned on. And there are many other examples: smart scales, again with Bluetooth. It's a bit complicated. Wi-Fi has a similar issues as Bluetooth for me. The BSSID uniquely identifies a device. Yes, you can change the MAC address or the BSSID of cards. MAC address randomization helps in this front. Smartphones, I think most of them since 2019 or 18, do MAC address randomization whenever you connect to an access point. However, things are still tracked. Wiggle.net, Google, Mozilla used to do it as well. Others are doing it. They're tracking access points. So whenever an access point is spawned up, they have people that are reporting that, hey, I can now listen to this new access point, and they're collecting it in a database. And so every time you turn tethering on your phone on, they've got a signal of where you were at that point, if someone reports the access point and it's nearby. Similarly, cameras, DSLRs often set up access points. There are many devices that from time to time will set up an access point that you might have on you that's also registered. On RFID tags, again, there was a talk earlier by NIP, and there was last year talk by Nemanja about RFID. Go watch them. I won't go into too much detail about RFID, but nowadays they're used for access control, for sharing information. They're used as anti-theft devices, athlete identification in races, tollways. In your car, you can use them in a tollway to access the tolls or access a garage area. There are 3 major versions. The one working at 125 kilohertz, they're very simple. They are not used so much anymore, I want to say, for a lot of things, for important things at the very least. There is well, important, that's it.
Still no.
Well, there is the 13.56 megahertz one, that's most of the things are nowadays. And then there is the higher frequency ones, where tollways, for example, for cars are, if you want something that's long range, you're going to be using the 900 megahertz, 868 megahertz one. And yeah, so again, go watch these previous talks. There are also some amazing talks by Christine Paget back in 10 years ago, I think. She demonstrated how you can read the long-range ones from more than 200 meters away, and how you can mess around with the lower frequency ones as well. Again, they are easy to detect the tags from a distance. You can also detect a tag being read, so you don't have to power the tag yourself. You might be able to detect a tag being read. And they're very hard to protect against these attacks. There are things you can do, but you're not completely safe. And this is an example of a ticket from Athens, from the public transport. If we look at it in the sunlight, we can see the antenna, we can see the chip. The problem with RFID is that it's everywhere. Like, it's in passports, it's in ID documents, it's tickets, it's cards, you can't get around it. You can't not have RFID on you, most likely. That's the problem. Moving on to other things that track us. Drones. So since January 1st of 2024, the FAA and the ESA, those are the Federal Aviation Administration of the US and the European Union Aviation Safety Agency, so the bodies that are responsible for aviation, mandate that drones need to identify themselves uniquely. They need to identify the GPS location, their location, and also they need to identify where the operator is physically on the location, on GPS. So this is called remote ID. The European mandate, I think, says that they have to use either Wi-Fi or Bluetooth. Most companies use Bluetooth long range. This is part of Bluetooth 5.0. And you can receive those signals with your phone. You can have an application that scans for Bluetooth long range and can decode the information sent by drones. There is, I think it's called Open Drone ID on GitHub. It's an organization, it has code, it has libraries that do all of this. And for the companies that are not following this Wi-Fi and Bluetooth part yet, DJI specifically, SDR projects exist that can decode popular alternatives. And now we will get to cars, which they are very interesting because the car industry has decided that cars need to have radios, lots of them in them. In the past, when you said radio about your car, you meant the radio that you listen to music to. Nowadays, cars have more radios than you can imagine. The industry term is vehicle to everything. X stands for everything. And the idea is that they want your car to communicate with other vehicles. That's vehicle to vehicle, V2V, vehicle to pedestrians, vehicle to cloud, vehicle to home, vehicle to grid, vehicle to infrastructure. So the plan is in the future, cars will be communicating with each other. For example, if one presses the brakes, let the car behind you know that it also needs to press the brakes. In particular now for Bluetooth, cars have multiple Bluetooth radios in them. The obvious one is the one you're using to connect with your phone, to share this, to be able to do telephone calls through your car speakers and to be able to display information on the infotainment system, GPS, Android Auto or CarPlay. Or you might have an OBD device, that's the onboard diagnostics, that's also using Bluetooth to get information about the car on your phone. You might have an RFID receiver or transmitter on your car because of tollways, because you have to access a parking area, or because you want to access a specific street, as we saw earlier in Belgrade. Or you might have a cellular connection in your phone, in your car, for safety reasons, so they can alert someone when you had an accident, or because they need to do firmware updates. And cars and firmware updates on the same sentence sounds very weird to me, but here we are. If you've ever seen this on the dash of your car, this means that the tire pressure of your tires is low. How does the car know that? So we've got TPMS, which stands for Tire Pressure Monitoring System. And the EU mandated that from, I think, 2014, every new car sold needs to have this system, needs to have a system to alert you about tire pressure. And it's possible to do this in an indirect way, to figure out the pressure of the tires based on various things, on the speed of the car, on how flat the tire is. But the easiest way to do it is to have an air pressure inside the tire itself. And because tires rotate and rotate at highway speeds, having cables and wires in them is hard. There are ways around it. There are slip rings. But anyway, it's hard, not important. What the manufacturers are doing nowadays is just putting sensors, air pressure sensors, with batteries in each tire and transmit that information back to the car. And, this is what this looks like. So this is a capture for one tire from a Renault device, from a Renault car. I've changed the ID, this is not the real ID, but you get a uniquely identifying ID for every tire, and you get the temperature of the tire, you also get the pressure of the tire, and for some fancy sensors, you might be also getting the acceleration of the tire, which is interesting. So for every car, you have 4 unique identifiers that the car is broadcasting pretty often. And this was understood that it was a privacy problem, but the mandates haven't been updated to mention something about it. However, the industry is moving on, and they're trying to use RFID inside the tire itself to lower this issue. And moving on, more wireless devices, because everywhere now. So smart homes. People are purchasing more and more things for the home to make it smart. There are multiple protocols and multiple different devices for interconnecting the appliances. Zigbee is a very popular one. It's working on the 2.4 ISM band, same as Wi-Fi, same as Bluetooth. It has various issues. There are some talks that you can watch about it, but the most important part is that usually it's trust on first use. So if you are able, when the device enters the network, if you are able to capture that key exchange, you can listen on everything that's happening on the network. Again, these devices are cheap, usually, so security is not the most important characteristic of them. And there are multiple others. There are doorbells, there are temperature sensors, smart plugs, blinds, all of them. Some of them work in unencrypted communications completely. You can receive them using RTL 433 for a lot of them. There are multiple devices in our homes that transmit who we are and where we are. Mouse, as I said, keyboards, mice, everything. And from smart homes, if you add a lot of them together, you get smart cities. And the EU is very big on those things. And initially, they mandated that they wanted to have smart power meters in 80% of the houses by the end of 2020. So a smart power meter is like your typical power meter, the thing that power comes from the company, and it matters how much power you are using, so they can bill you. In the old ones, someone has to go and take a reading, read what the value says, and send it back to the company, so they can bill you. The idea with smart power meters is that the meters are RF capable, and they can communicate this back to the power company on their own. And in theory, that's good because it's easier. You can get automatic fault detection. So if a power outage happens, the meter stays on for a couple of seconds. So it can alert the power company that, hey, the power is out. You need to come and fix this. This is called AMI, Advanced Metering Infrastructure. Again, Europe is big on this. And the protocols that these smart power meters use, it ranges. They can be Wi-Fi, there can be something custom. It might be Zigbee, it might be LoRa, it might be something custom that's mesh. And sometimes they even have central collectors that collect all this data and send it back to the company. And these are pretty beefy. They even are Windows machines sometimes with SSDs in them. So they are not just simple devices. They are very complicated. And smart meters also have other privacy issues. Depending on the granularity of the data, of the readings, it can be very important for privacy. There are multiple papers published that say how granularity affects the privacy. And one of the scarier ones for me says that if the granularity of the readings is between half a second and a second, the power company can understand which TV channel was playing on the TV, based on the television, based on side channel analysis of the power usage at the home. So if nothing else is changing in the home and you have power fluctuations based on what's playing on the TV, they can figure that out. They were able to replicate that in a lab. And on the smart cities, it gets creepier for me because this is the important part. We said that we have Bluetooth. We said that we have Wi-Fi on us with our phones. We said we have Bluetooth smartwatches, headphones, whatever. Bluetooth is currently tracked. Simple as that. Back in 2009, the city of Houston in the US wanted to figure out a way to measure the traffic on its streets and measure the congestion. So together with the Texas University of Transportation Institute, they figured out that they can use Bluetooth to track cars, they can use Bluetooth to track pedestrians, and they started doing that. So this was back in early, I think, 2011, and the website was up until 2015, where they said how it's working exactly, that we're tracking Bluetooth, that it's anonymous because the Bluetooth ID doesn't tell us who you are, just uniquely identifies you. And they had this very nice quote that if you care so much about your privacy, you can just turn off your Bluetooth devices. And I find that very weird. AWAM that's described there stands for Anonymous Wireless Address Matching. That's the industry term. I believe there is a rich industry that seems very localized. So I think from my research, there are companies popping up since the mid-2010s in various parts of the world that do this. For example, in Canada, there are Canadian companies that provide this as a service to the city. And they boast that we track Bluetooth, Bluetooth Low Energy, Wi-Fi, and a couple of other protocols. And we are able to identify people and cars with better accuracy than others. And there are multiple different names for this technology. Bluetooth Journey Time is the common one. This is an example taken from a city in the UK. They decided to try it out. They put out 130 sensors. Every blue dot is a sensor, is a Bluetooth sensor. So Bluetooth is currently tracked. Wi-Fi is currently tracked. They say they anonymize this. They say that it doesn't uniquely identify you because they can't pair your name with the ID, but it still uniquely identifies your path through the city. And in conclusion, this is not science fiction. This is happening right now. This has been happening for the past 10 years. And RF and the wireless technologies, they are everywhere in our life nowadays, and they have increased technological complexity by a lot. The typical example for this are headphones. If you have a wired headphones, they might have 1, 2, 3 transistors in them or none. If you have wireless headphones, you have the Apple AirPods. The latest model has 1 billion transistors in them. So the difference between 5 transistors and 1 billion transistors is crazy to me. And finally, it's a battle of privacy versus convenience. At the beginning, I said that the RF world is invisible. Because of this, it's hard to understand where and how much we're using RF daily and how it's impacting us. However, in the past, we worried a lot about surveillance through cameras in particular. We still care about cameras and cameras surveilling us. But I think it's time that we understand how much our privacy depends on radio frequency and how much we're giving away in the name of wireless convenience. And that's it from me. Any questions?
About the congestion tracking thingy, did they actually write down, did they identify the IDs? Did they write them down, or did they just count in the last 5 minutes we saw that many Bluetooth IDs? So we assumed there were there was one person or something.
So the idea there is that they track the ID throughout the city to know how long it took you to travel from one point to point B and get more data out of it.
So they actually identify individual devices and see where you move.
Yep.
Okay.
They say it's anonymized and it's cryptographically, I guess they're hashing it just, but it's still, they have the hardware to do that throughout the city.
Hashing is very complicated for
Yes?
Okay, it's just a random question. You mentioned that in Greece they tend to hide the base stations for cell phones.
Yep.
Some time ago, 10 years ago, I watched some low-budget Greek movie about the specific thing where they hid a base station inside an apartment building, and supposedly people living around it had no idea, and they got very, very sick. So, is that a conspiracy theory? Was that real? Do you know anything about that?
I don't know the particular movie. I know we are hiding them, so you can see them at some places. They are visible, but in general, we tend to hide them. I can only say that the research shows that base stations don't cause any issues to us, to humans. From my understanding of the physics, they don't, so not sure what to say other than that.
Thanks.
If you're not close, as usual, as always, it's important. The important part is how strongly the antenna radiates, how strong the power coming out of the RF, and how close you are to it. As you get further away from the antenna, the power dissipates very quickly. So as long as you are not right next to the antenna, even if it's radiating with a lot of power, you are usually fine.
Also, you said something about tracking emissions from, like enforcing the tracking of emissions from individuals that when you're not allowed to emit, if you emit something like that. Would it be viable to have a highly directional antenna and let it bounce off something else like a kilometer or two away and use that as the actual and as a reflector for your signal to obscure your position? Would that work? Something like that?
Don't you want to use your devices? The whole point is that if you send the signal somewhere...
I was talking about something like it was rather the regulatory part of the spectrum where you have the where, I don't know, pirate radio and stuff like that is an issue.
Okay, so can you repeat
in Germany there are like famous tracking vehicles that roam around the neighborhood if you emit in some shitty frequency. More often than not, those are like D-line adapters, which are apparently pretty terrible in the radio spectrum. But if you wanted to hide that, would that work to hide your location that way? If you're broadcasting something that...
So transmit with a directional antenna somewhere?
Somewhere that is a reflector, like let's say a satellite dish 2 kilometers away and use that as a reflector and to transmit to the city, yeah.
Yep. I want to say that they used to do this, but I'm not sure.
Okay.
I want to say that the max, what is it? I don't remember the name, Max Headroom incident in the US back in the 1980s. We can discuss about it afterwards outside because I think they did that, yes. Any other questions? Okay, perfect. Thank you for coming.